Sorry, give me a second here. Okay. Usually it warns me that I'm recording, but that's fine. Sorry, I'm having a little Zoom trouble here. 1 second. Okay, perfect. All right, so last class we were talking about, we were actually in a programming example, and we ended off by compiling an object file and then linking that to an executable. But in that case, the object file and the executable were the same thing. So here is, I have the virtual machine all set up here, and I have, here, sorry, that's not what I wanted. Okay. We have the virtual machine all set up here, and here I have my shell that I can compile and execute commands in. So if I list the contents, I see that I have my source file p1.cc, I have my object file p1.o, and I have my executable p1. What is happening with it? Sorry. So yeah, Linux is good at a lot of things, but Zoom apparently not one of them. Okay. All right, so we have those. Let's, yeah, just as a brief review, I'm going to remove the object file and the executable. So now we just have our source file again, our source file where the code is listed over here. All right, I guess I'll just leave it like this. Sorry, Zoom troubles. So now I can recompile it either directly using this. So -o for output, p1 is the name of my executable, and p1.cc is my source file. And then if I run p1, I have hello COMP2404. The other thing I can do is compile it to an object file. So -c p1.cc. I don't have to specify the name of the object file. It does that on its own. That's p1.o. These are both source code, but there's, this is usually, this has to be linked in order to be an executable. So then I can say -o, p1 is my executable, and then p1.o is my object file that I want to link. And then I can execute, and I have, yeah, hello comp2404. All right, so that's just a short review of last class. Any questions before we start looking at some of the other stuff here? Okay. Yeah, no. Okay, so what happens when we want to run a C++ program? Well, we write the source code, and then we put this, send the source code to the compiler. The compiler builds it into an executable. So this is the straightforward G++. And then we can run that executable. This is what is understood by your computer. Your computer can't understand this, but the compiler is like a translator, right? It takes the source code and all of the syntax that we very carefully wrote and converts it into something that basically machine instructions for your CPU. So yeah, the idea behind these object files, as we saw, is that as programs get bigger, we want to keep them modular. So we're going to have a bunch of different classes or pieces of source code. We can compile them into object files and then link them together. Right, so the pieces of source code that we link together are called object code. So object is machine code, but maybe I reference a function, but I don't have the implementation of that function available. All I have is the function prototype, so that the compiler knows that I've used it correctly, but the compiler, it doesn't, when I compile it into object code, the code that's supposed to be run is not there. I have to link to that code. right? So object code is machine code, and maybe we're missing a couple addresses for certain function calls. So let's take a look at a slightly more complicated example. So I'm going to make a new directory here. We'll call that P2, and then we will copy, let's say, the source code into P2, but we're going to call it foo.cc. Okay, so now we're going to change directory into P2. So now we can see there's a new directory here and foo.cc, which is simply p1.cc copied over. So we'll say foo.cc. And then, yeah, let's see what. Okay, so we still have our include IO stream. We can compile it into .o into an executable called foo, and then run foo, and we get hello COMP2404. Okay, so far so good. What we want to do now is break this down into, we want to make another function call. So we're going to write a second function. We're going to say hello world here. We're not going to end this line. And then we're going to call a function that we're going to write called foo. Okay, so what is this function? Well, we're going to write it. So what we can do, it has a void return type, open brace, close brace, and the arguments go in here, but there's no arguments in this case. And all we're going to do is say from COMP2404 end line. Okay, so let's see what happens when we try to compile our program now. Okay, so I'm getting an error here. It says foo was not declared in this scope. So our compiler, as I said, it's kind of primitive. When I write a function, so we call them functions in C++, we call them methods in Java. They're the same thing essentially. When I do this in Java, the Java compiler actually reads ahead, recognizes that there's a foo function. So then when I call it here, it's not surprised to see it. But the compiler in C++ is actually quite literal. So it starts reading here, and it goes down, it reaches this foo function, and it says, I've never seen this before. I don't know what's going on. So you have to tell me about this function. So there's a couple ways we can handle this. We can take this function declaration and put it above the main function. And then the compiler will read through starting at this line. So it reads everything in IO stream and says, okay, I know about all of those functions using the namespace standard. Here's a foo function. Fine, I'll remember that. And then when it gets to the main, everything should be okay at that point. So I try and compile now, and it works. And I can run it, and it says, hello world from COMP2404. Okay, so that's fine and good. So we're calling now functions, we're calling lines of code from other parts of the program. In here, it's in the same file. We can do the same thing for different files. Okay, so which we're going to do, but before we do that, this is actually discouraged in C++. We don't want to we want to have the first function we see to be the main function. So generally what we do is we say, well, we put our additional functions below main, but we're going to tell the compiler about this foo function. So I'm going to say, hello compiler, there's a function called foo. It has a void return type and no parameters. All right, so this is called forward declaring. I wish this was a little brighter, but forward declaring of a function. So I'm making sure that the compiler knows about it before I use it. Okay, so let's try now recompiling that, and voila, it works. Hello world from COMP2404. So this is for declaring, this is considered good design. Okay. All right, questions so far? Okay. Now let's say maybe we want to call in a function from somewhere else, but maybe it's in a different file. So what we're going to do is we're going to make a file called, let's see if this will work. All right, so perfect. Now we have a file called foo2.cc. So now we want to put a function in this file. Now we're gonna put all of this extra, include IO stream. We're going to include that. We're going to put using namespace standard. We'll try it without it, but for now we're going to put it in there. And then we're going to make a function called foo2. Nothing fancy. It's simply going to do the same thing. Cout from COMP2404 in foo2. Okay. So now if we go back to our original code, we can close this, I guess. So now instead of calling foo, we want to call foo2. All right. Now, obviously, the compiler doesn't know about foo2. So how can we tell the compiler? Well, there's a couple things we can do. One way to do it is just simply to include it. So if I say foo2.cc, what the compiler is going to do, it's going to start reading here. It's going to get down to this include statement, and it's going to jump to this file, read everything here, and then jump back here and continue reading. So when I say include some source code here, which this is bad form, but of course, as in everything in C++, there's the correct way to do it, but C++ lets you do whatever you want. So don't do this, but know how to do this in case you have to do this. Know what the compiler is doing. Okay, so now technically this should work, but let's see if I've made a mistake or not. Yeah, so foo, hello world from COMP2404 and foo2. So that worked exactly as we wanted. So that's one way to get code into your program that's in another file. But this is bad software engineering for a couple of reasons. One, every time I compile it, it recompiles everything. So if I have a large program, that's going to be very slow. So there is a better way to do that. I can take this out and I can tell the compiler there's a foo2 function, but instead of including it, I'm simply going to link you to it. All right, so what I can do is then g++-c foo2.cc. So now I'm going to make an object file out of my foo2 program. Okay, so now I list it. I have foo2.o. So this is machine code, but it's not executable yet. And now I'm going to link it to my original foo. So I say g++, my output file is foo, and then I want foo.cc and foo2.o. Okay, so now when the compiler reads through, I forward declare this piece of code. So the compiler knows there's a function called foo. It knows the function signature. So when I use it here, the compiler is like, okay, that's fine. I don't know what goes in here yet, but I'm okay with you making this, this call. And then when the compiler goes to put it all into source code, the executable, it goes to the object file and says, this is some empty address, and it supplies the address for this source code here. So let's run it. So hello world from COMP2404 and foo2. And we could even get a little bit fancier with this. So let's say I remove foo and foo2.o. So I can say g++.c. So I make an object file out of foo2. I can make an object file out of foo1. And then I can link them both together into my output file. We can call this p2, foo.o and foo2.o. And then run p2, and I have my executable. Okay, so that's all of your programs. Yes, you need to make object files to link. But that's actually a really good question. I wonder what would happen if we did this. Let's say output file test. Yeah, it was fine with that. So yeah, this is of course not linking. This is compiling everything together. But yeah, when you're doing linking, you're using object files. And the advantages is that I don't have to recompile all the code. I just have to recompile the object code, and the linking is faster. All right. And yeah, that works too. But in this case, I've compiled everything together. So if I make any changes to these files, I have to recompile everything. I have a bunch of executables at this point. So I have P2, which I made through this. I made my two object files and then linked them into an executable. And then I have another executable called test, which is compiling everything together from scratch. So yeah. The Makefiles, right? So yeah, your Makefiles are going to consist of a bunch of these commands put together, if that's what you mean by README. Compile it. Yeah, no problem. No problem. Okay, we will go over it again. Here, let's go over the notes, and then I'll come back and we'll just redo that example again, but after we look at it. We sort of look at the theory behind it a little more. So program building is translating source code into machine code, right? So that's all we're doing every time we do -c. We're compiling it into an object file. That's machine code. When we compile a .cc into an executable, that's also machine code. The difference is there's a couple of flipped bits somewhere, and the executable, it knows where all the code it needs is. So we take our source code, which is our C++. It's basically instructions written in a high-level language close to English. Your computer does not understand this stuff, but the compiler takes it, converts it into machine code. And basically these look like a bunch of numbers, and it can be understood by a CPU. We'll see a little bit later how we can actually compile. We can compile it into assembly code to give you an idea of what the machine is doing, or what the compiler decided to do with all of this stuff. So program building is the making of an executable from one or more source files. So the executable is the end result. This is the thing that runs. When we make an object file, maybe not all the code is included. Sometimes it is, but for the executable, all the code must be there. So this is a binary file that can be understood by, basically it's a set of instructions for your CPU. In general, executables are not portable, right? Unless we're running on the same OS and similar architecture. You can download binaries for, Ubuntu or for Mac or for Windows, and they generally run pretty fine. You don't have to compile everything all the time, but also compiling on your own machine can optimize certain things. But so a program compiled on one platform will not work on another platform, right? We can't compile in Windows, run on Linux. We can't do vice versa, or with Mac OS. So typically, my executable will contain code from many sources, right? Especially if it's, we're writing little toy programs here, but for real programs that really do things, there will be plenty of sources. So there'll be our code, there'll be other people's code, there'll be libraries, standard libraries. But for each binary, there is one main function, right? That's where your code starts for each executable binary. Okay, so compiling turns C++ code into object code. In general, we want there to be a one-to-one correspondence between C++ source files and object files. That's the most efficient way to do it. That way, when we have to recompile something, we recompile as little as possible. Because linking is much faster than compiling. Linking connects all of our object code together. Right, so our source code might call a library function or simply a function from a different file, as we saw. Yeah, so when I'm compiling a piece of object code, all I really need is the function signature, right? So we saw I compiled my foo into foo.o. The compiler saw, right? The compiler saw that there was a function foo2. It only knows the signature. At this point, when I make it into an object file, it does not know what the code is. It doesn't know what the code is until I linked it in this step. So yeah, all I need is the signature in order to compile a piece of object code. Yeah. Executable code for the library function is a different object file. Yeah. So also the cout object, when I imported the IOStream library, of course, that just gave me access. It gave me a bunch of function signatures, and then the compiler in the background links those object files to our program. It does not recompile them. All right. So now when we're compiling, it's going to look closer to this. We're going to have a bunch of source code files that we've written, and then there will be some pre-compiled object files, maybe in the standard library or maybe in some code that somebody else wrote. These are just object files. I don't need the source code. I just need the function signatures so that I know that the compiler knows that I'm calling them correctly. Then the compiler takes all of this object code and links it all together. Or sorry, the compiler compiles all of our source code into object code. And then the linker takes all of that object code and links it together into an executable. Basically, all it's doing is saying, when you call this function, jump to this memory location, and that's it. So that's a lot faster than compiling. And in the end, we're left with a program, right? A complete binary that I can run and that that the CPU can understand. Okay. So compiling a single file, a single executable without using object files is G++-O for your output file, and then put in your source file or source files. We can compile a single file into an object file, and then, we link it to itself, which basically just flips some executable bit somewhere. But most commonly, we're going to be compiling multiple files using object files. So we're going to, here we'll make two object files, and then we'll link them together into the executable. That way, all these compilation steps are separate. Okay, so somebody wanted to review all this. So we'll go over these examples again. Okay, so I'm going to remove test foo.o, foo2.o. Okay, so now I have, remove p2. So now I have my two source files, foo.cc and foo2.cc. So there's a bunch of ways I can compile this. In foo.cc, I make a call to foo2, but I did not include the source file, so I'm going to link to it. So what I want to do is I can compile these both into object files. So I can start by compiling foo.cc into an object file, which is fine because all the compiler needs to know is the function signature, and then it can verify that I'm using it correctly. It does not know the source code for this yet, but it doesn't care either. So I can compile my original foo.cc into an object file, foo.o. So this is binary code that that your CPU can understand, but it's not executable at this point. For one, it doesn't have the proper bits flipped. For two, there's a piece of code missing. It knows foo2, it knows the signature, but it doesn't have any code to put in there yet. So I can say, well, let's compile an object file for foo2. So this supplies the foo2 function. I have now an implementation here. I compile that into object code or into machine code if you prefer. So now this is a set of instructions that the computer can understand. It can put it in memory somewhere. And then when I call foo2 in my foo, it can point it to it. How do I link those two memory locations together? Well, I compile those into foo, and I link just by putting them as arguments, foo.o and foo2.o. Okay, so now when I list, I have my foo executable. So now when I make this call to foo2, the compiler has pointed it to the proper memory location for the instructions, and I can call it. Okay, so we're going to, yes, this is essentially how we're going to be handling compiling in this class. So, right, questions? Okay, now, once we get to a lot of files, of course, this can be a pain, right? So how many, if I had 10 source code files, then, I need to compile 10 of these object files, and then I need to link them all. So every time I want to, recompile, well, if I happen to make changes in all 10 files, then I need to recompile each part. So in order to make our life easier, we use Makefiles, right? So compiling and linking can get complicated pretty quickly. Makefiles can help us keep this process organized. So all a Makefile is a text file of compile commands as well as dependencies, right? So what does that mean? Well, the compile commands we've seen. So it's going to be G++, -C something something or -O something something. But for each of these files, each of these compile commands, we're going to list the dependencies. And when I run make, these files will only be recompiled if the dependency file has been changed since the last time it was compiled. All right, so we're going to see an example of that. One thing to note, we're going to introduce you to a clean command. So sometimes these dependencies, especially in this, we're not being super careful about our make files. I just want you to get used to the idea. So what can happen is that depending on what order you compile your object files in, sometimes you can get into a situation where a file has not been recompiled properly. So sometimes just deleting everything and then recompiling can fix a broken dependency, right? So if you're having trouble compiling something, sometimes it's worth cleaning. Now, the idea behind a makefile is we don't want to recompile everything, but for our purposes, sometimes that's the solution. Okay. So a makefile would look something like this. So I have a make command. So I'm going to write or type in my terminal make foo. So what that's going to do is it's going to look for a file called makefile. And if it sees it, it's going to look for the foo command, and then it's going to execute that foo command. So the foo command is this. Well, first of all, yeah. So it goes to this command, and then it looks at these two lines here. So the first set of files are the dependencies. So I'm saying execute this command only if these files have changed since the last time I compiled this file, right? So this is not, although we often use the file name, this is simply a command, all right? So, oh yeah, this is, and that's actually wrong. That's hilarious. Okay, so this is the list of dependencies. If either of these two files have been changed, then we're going to execute the foo command. If either of these are changed, then this is the command that gets executed, and it's of course wrong. This should be .o foo and then foo.o foo2.o. All right, so I'm missing the output file here, but yeah, so that's the command that gets executed. All right, let's look at an example and then we will come back to this. So let's go. So we're going to make a directory called make. We're going to copy everything from P2 star to make. So let's, all right, so we got everything in there. So cd into make. Okay, so now we want to make a file called Makefile. So I'm going to add a Makefile this. Okay, so now we want to, here, let's actually, let's start simple. So I'm going to copy p1.cc into make. Okay, so I have my p1.cc here. This is a standalone program. So now I'm in my make file. I'm going to say, I'm going to give it a command called p1. I'm going to list the dependencies. Well, the dependency is p1.cc. And then on the next line, I'm going to give the command for compiling that. So I want to output it to p1, and my input file is p1.cc. Okay. Wait, there's Makefile. Okay, so now I have a Makefile. Just ignore all the foos for now. So when I run make, it's going to look at this command, and I could say make, or I can say specifically make p1. Right, so it executes this command, and now look, I have a p1 executable. Hello, COMP2404. Okay, that's great. Let's say I also want to make foo. So the dependencies will be the two object files, foo2.o, and then the command is dash output to foo, and then foo.o and foo2.o. So I'm going to link those two object files, but only if they've been changed do I need to rerun my my foo command. All right. However, I also want to make sure that these object files are there. So I will say if foo2.cc, the source file, has been changed, then I want to compile this into an object file. And also if foo.cc has been changed, I want to recompile this object file. Okay. So now when I can call make foo. Okay, so that didn't, oh yeah, because I didn't change the object files. So all it had to do was link. That's not what I wanted to do. Food. Oh, I have two. Yeah, sorry. Let's make this .o. So yeah, it compiled my object file because I named my commands, both commands, foo. Oh yeah, so cp p1.cc was, I just made a copy. Yeah, sorry about that. I copied p1.cc into the make directory. Right, so yeah, I had outside of this directory, I had p1.cc. I just wanted to make a copy of it inside so that I could run this example. Yeah, so a couple of the commands that I've been using that I guess I did not really explain. CP is to copy a file. If I want to move a file, it's the same as copy, except it deletes the old one. So I'll say, p1.cc into p1 backup.cc. And now when I list, I have my p1.cc is gone, but p1 back.cc is there. So I can move it back to the copy command copies. What else did I use? Make directory. If I want to make a new directory inside the current directory. p1.cc is a dependency of p1. Yes. So in my make file here, I've listed it as one of the dependencies, well, really as the only dependency. So yes. Yeah. Any other questions? Okay, so let's see here. Let's try make foo again. Okay, so it went through and it linked those two and it recompiled my executable. So now when I run it, it says, hello world from COMP2404 and foo2, just like it's supposed to. At this point, if I run make foo again, it says, well, foo is up to date. And I can actually make, I think if I say make foo2.o, that is also up to date. Let's say I removed foo2.o and then I called make foo. So make foo says it depends on foo2.o. Foo2.o is compiled using this. So since this file doesn't exist, the make file will actually look to replace it. Right, so yeah, this is, sorry, let me see here. No, anyway, yeah, that's fine. I'll have to, there's a couple things I want to, it's always fun to try and experiment with things and see if you can break them and see what exactly is happening. But you don't want to go too deep down that rabbit hole because you can be here all day. But yeah, so anytime if I happen to remove my object file or if I recompiled it, right? So I've made my foo executable now. Let's say I go to foo2 and I say, but different. So I've made a change to it. I've saved it. If I look at my make file now, foo2 depends on foo2.cc. So this should get recompiled. When this is recompiled, this will change, and then foo should also get recompiled. Actually, this might not work. Yeah, foo is up to date. So I have to recompile foo2.o. Yeah, so there's, yeah. Anyway, let's say make foo2.o. Oh, it shouldn't be. What happened? Well, that's interesting. It's always fun when things break. Foo2.o is up to date. Um, all right. That's a little weird. I'll have to look up what's going wrong here, but this should be updating. So I'll continue on for now, but maybe oh, am I in the wrong folder? Yeah, you're probably right. Ah, thank you. Ah, it's nice to have a second set of eyes. All right. Perfect. Thank you very much. So let's try that again. Yeah, so it recognizes that somewhere down our dependency tree that something has changed. So it goes through and recompiles all of the necessary parts for you. Yes, thank you for that. Yeah, cool. Questions? Yeah, I'm in the wrong. All right. So the other thing we like to add to our make files is I can make a clean command. All right, so there's no dependencies for this. All I want to do is remove -F to force, and then I'm going to remove my executable foo p1 and any object files. So this is if I'm trying to compile and things aren't working, and I want to recompile everything from scratch, I can run this make clean, and it removes all of my executables and object files. So now I'm back down to source files, and I can make foo again. And the other thing I might want to make is an all command. So yeah. So I'll make p1 and foo. So if I say make clean, and that will go through and make everything for me. All right, so my dependencies are these commands here. And then it goes down the dependency tree and checks everything. So this is a basic Makefile. So every time you make a Makefile, generally speaking, you want to make all, although sometimes maybe not. Maybe you want to keep all of these separate. If you're making one executable, then or if you're making multiple executables, then sometimes it's nice to have all. But you definitely want a clean command as well. Sometimes things go wrong, the dependencies break, you can't figure it out. Try running a make clean and then rebuilding everything. That can sometimes fix your problem. Now, that's not the optimal solution because that means, but we're at a level where we're still discovering this stuff. So how to manage your dependencies so that you never have a problem is not actually that trivial. You have to really pay attention to the dependency tree. Okay. Questions? Can you explain what all does again? So all is going to check these two commands. And so it's going to go to P1 and check, does P1 need to be recompiled? Well, it's going to check P1.cc. Has that been changed? So if I run make all again, it says nothing to be done for all. So it checked all the dependencies and said, everything's fine. If I go through and I made a change to P1, okay, so now P1.cc is changed. I run make all. It checks the P1 command and sees that, hey, this should be recompiled. All right, so make all looks at these two. That's a good question. I think so. Let's try everything. Probably. I think all is just a convention. Yeah, so there we go. But this is one of those things where you can substitute other things, but it's not recommended. The reason being is that if somebody reads your Makefile, this is what they expect to see, right? So if you put everything instead, they're going to be confused. So yeah. So yeah, Makefiles are actually almost everything in C++ is pretty primitive. If you ask, can you do it? The answer is probably yes. So I can rename these. I can use my include to include source code, although you shouldn't do that. I don't know, these are all very primitive, which means that you can do pretty clever things with them. You want to be wary of one way to crash your computer is to have, so if this is dependent on, let's say I did this. So this is dependent on foo and foo is dependent on P1. That's, I accidentally did something similar to that before, and I had to restart my computer because this is an infinite loop now. It just recompiles and recompiles and recompiles. That may not be exactly how I did it, but there was some Makefile run it. The thing is, I would have to restart my computer. Maybe at the end of class, I can try that. It was something like that. I don't know if that was exactly what I did, but I had some circular dependency that my computer froze up and I was like, what's going on? And then I had to kill it, but even killing it didn't help. Everything was, I don't know. Anyway. All right. Okay, so here we have make all. So here I only have the one, but you can put as many commands in there as you like. And yeah, so this is pretty, yeah. I'm curious about this. Is this reading the file or is this reading the command? What if I did? All right, I am going to do a little experiment here just for fun. So what if I made this, let's say P1 test, but I'm still going to compile it into P1. So I can say make P1 test. Okay. Make all, nothing to be made for all. So if I change this, and again, and then I run make all. Yeah. Huh. What the heck command is that? All right. Well, it looks like maybe I broke some. All right. I don't want to mess around too much with this. I thought something. The make file is up to date. The make file is up to date is not a problem. That means you haven't changed anything. But if you have changed something, then you need to look at your dependencies, right? You have to make sure that you've listed all of the files that should be changed or the commands. Sorry, I just want to try one more thing here. That was a really strange result. So it appears this dependency will look either for a file or a command, which is kind of, did it do that right? Yeah, okay, cool. So yeah, if it says it's up to date, that's not necessarily a problem. I don't want to do that. It just means you haven't made any changes or your dependencies are not proper. All right. Other questions? No rule to make P1 test needed by all. Stop. Okay. So yeah, it looks through for a file or a command, and if it doesn't find either, then it gives me an error message. Okay, so somebody's asking about the star.o here. So yeah, this is the match anything regular expression, right? This is the wild card. So all I'm saying here is remove all files that end with .o. Right? If I wanted to say, let's see, I could do something, for instance, I'm not going to do it, but I could say foo star. So if I said remove foo star, this would wipe this one because the star matches everything. It would remove this one. It would remove this one. Anything that started with foo, any file that started with foo would get removed. So yeah, it's a regular expression. It's a wildcard expression. So it's saying, in this case, I'm saying remove all .o files. That's all. Other questions? Okay. Yeah. So they're make clean, and the dash F is the force. So I want to force it to remove stuff. In some cases, certain files are protected, but I'm just saying, no, go ahead and remove everything. And yeah, so example P3, which we've just got finished doing. Is that, yeah, this is the last of this one. All right, so that's an introduction to the basics of getting your C++ code up and running. All the way from Makefiles, all the different ways we can compile. As I said, when you write your code, I expect to see something like this with an all command and a clean command. And also, sorry, I just drew a complete blank. So we have the Makefiles. Ugh, I don't know. There was something else I wanted to see. Anyway, that's fine. All right, so we'll move on to the next topic here. We have about half an hour left. So some of the basic language features we're going to talk about. So this is, we went over the fundamentals of compiling your program, but now we'll look at actually, some of the syntax and things of C++ that you should know. Probably you do know because it's all very similar to C and Java, but it's worth going over again. This is, of course, I don't know. I made these slides over the summer and I thought this would be funny, but essentially C++ is, the wild, wild west of programming. So you don't get anything, you don't get any of the comforts of other programming languages. You have to do everything yourself. So a short history of programming languages, programming goes all the way back to the 50s, right? So in terms of, I guess, disciplines or, sciences, it's pretty young. Computer science is, this doesn't seem young to you. That's like 70 years ago or whatever. But that is pretty recent. So it started off with assembly, which we don't learn anymore, but, it is pretty interesting. Fortran, Lisp is one of the earliest languages. It's very, Lisp is very cool. You'll see a version of it, Scheme, in 3007. It's, once you get the hang of it, it's very fun to use. COBOL, which is still being used in, is it banks? I forget. I get COBOL and Fortran mixed up, but BASIC in 1964, that is what, I wrote my first program in, is BASIC on the Commodore, on the VIC-20. B came around in 1969, which was the precursor to C, which came out in 1972. Scheme and Prolog, which you will use in 3007, come from the 70s. C++ came out in 1980. It was originally called C with classes. In 1983, it was renamed to C++. And then Ada, which is, what is that? I forget. Is that used in the military or for NASA? I forget. Objective-C in 1986. I think iOS now uses Swift, but, as it wasn't that long ago that they were actually using Objective-C. Perl, Haskell, if you take 3007 with Professor Doug Howe, he uses Haskell, I believe. Python 1990, or Java 1995. So 1995 is the sort of, Java is one of the youngest languages, but all of this stuff evolves pretty quickly. So C++, it's from the 80s. So you might wonder, what is the most powerful language? Well, it depends on how you define power, right? So a Turing complete language, which all of those are, the set of problems that you can solve is the same for all of them. So the difference between programming languages comes down to speed. Sometimes you want things more efficient, convenience, whatever libraries are available, compiled versus interpreted, that can affect. An interpreted language is, of course, portable, because I can write an interpreter for every different machine and then just run the same code on them. Whereas compiled is not as portable. So yeah, the differences in these languages, some are fast, some are expressive, some attempt to do both. But yeah, all programming languages manipulate data. Computer science is the science of manipulating data. So let's look at what data is. So in C++, we have what are called primitives. So integers, floats, doubles, characters, bool, which is short for Boolean, which is a true or false. So all of these are about the same size. They are between, depending on what your system is. So most systems now are 64-bit systems, which means the address bus is 64 bits wide, which means Well, actually, I think integers are still 32 bits. Yeah, I'd have to, that's one of those things I always have to look up. Are they 32 bits? So then a long is 64 bits. A double would be 64 bits. A float would be 32. Yeah, you're probably right. I don't know. I should list this here in the slides because I never remember offhand, or at least I never remember correctly. That's true. It can vary between platforms. Although I think you can specify if you want integers to be 32 bits. Yeah. Other data types, user-defined data types. You can define structs or classes. And then, of course, one other data type is a memory address, like a pointer or a reference, which we will get to shortly. So in your computer, all memory looks the same. It's just a bunch of ones and zeros, right? These are just numbers, and in particular, they're binary numbers. So when a computer looks at a memory location, it does not know if it's a double, an int, or a char, a character, right? So how we manage that is that, well, C++ is a strongly typed language. So we have our memory is pointed to by another piece of memory, and that other piece of memory has a label that tells the compiler what type it is. So when the compiler looks at this, it knows, I should interpret that as a double, or I should interpret that as an int or as a character. Right? So this pointer also has a memory address, right? And C++, of course, lets us manipulate these addresses as well as values. So you can use things like pointer arithmetic, right? Which means I can add one to a pointer, which will make it point to the next memory location. All right, so variables. Variables are basically things we use to store data in our program. So they have a name, that's their label. They have a type, right? Again, it's a strongly typed language. They also have an address, and they have a value, which is the value that's located at that address, interpreted according to whatever data type it is. Okay, so I mean, you should all, of course, be familiar with variables, but just as sort of, we want to break it down to its lowest level, and so we know exactly what's going on when we do clever things like pointer manipulation. C++ supports structs. So structs can have variables and also functions just like classes. By default, the members are public. All public members are considered bad software engineering. Now, again, you should put an asterisk next to this because it depends on what your needs are, right? Sometimes you just want a completely transparent, I guess, data structure that has some function attached to it. In this class, though, we're not going to use structs. All right. I want you to, we're trying to teach you good software engineering like encapsulation and the principle of least privilege and things like that. So structs don't use those things. Sometimes that's the right decision, but for us, we're going to stick with classes. We're going to focus on classes and learn how to use them properly. So classes, as in, like in Java, they contain member variables and functions, right? So they have data associated with them as well as operations. All members are private by default, right? So we'll look at access modifiers in detail later on, but of course, hopefully you are all familiar with private, public, and protected, although they mean slightly different things in C++. So our classes and classes in general follow the principle of least privilege. That means we want to hide everything we possibly can, because if we don't, all the things that we don't hide, all the things that we don't make private, when somebody uses our class, they assume that they're supposed to use them. And sometimes we don't want them to because they can mess up the internal functions. They can change some data they're not supposed to. So the principle of least privilege we're going to use to sort of protect our classes and their functionality. All right, so we can manipulate data using operators. So the types of operators, we have arithmetic operators or arithmetic operators. So plus, minus, multiplication, division, the modulus. This is increment by 1, and this is decrement by 1. We have relational operators. So these are logical operators which resolve to a Boolean value. So when I use a relational operator, this will resolve to either true or false. Ooh, I'm trying to remember. I always forget if it's a capitalized in C++ or not. I mix it up with Python sometimes. We have logical operators. So these take Boolean values and combine them, right? So this is the and, so true and true equals true, for instance. True and false equals false, etc. This is the or, the logical or. So true or false equals true. False or false equals false, right? This is the negation operator. So if I put not and then some Boolean, it'll change true to false and false to true. Bitwise operations. I can't remember these. That might be, I would have to look them up. I know the and just does a logical and on all the bits. Is that a not? Yeah. But yeah, so it's a not, but what is it? Does it flip every bit? Or do you have to specify the bit? I can't remember how that works. I would have to look it up. So we're not going to use many of these, but every bit, cool. So and if I and two, I mean, this is probably we don't need this, but if I do and these two numbers, then is it this? No, it's all zeros, right? Man, I can't remember. It's been a while. Is it all zeros? Yeah, so I think it does a logical and on all of these, which means that 0 and 1 equals 0, 1 and 0 equals 0. All right, so if I used or there, then this would all be 1, 1, 1, 1. Anyway, bit shifting, and this is that, yeah, again, I'm a little out of practice on these. Is that exclusive or? Excellent. All right, we're not going to use many bit operations, but bit operations are cool if you really want to optimize something, you can, sometimes bit operations are a nice shortcut. Assignment operators. So I want to assign a value. I want to add a value to a value and then assign it. I want to subtract a value from a value and then assign it, etc. Conditional operators. Arguably, this is a control flow statement. This is essentially if something, then something else, but it's shorthand, right? All right. Okay, so let's take a look at some examples here. How are we doing for time? 10 minutes left. Okay. All right, so let's go back to our machine here, and we're going to, oh, that's not what I wanted to do, sorry. I want to go to 2B. All right, excellent. Okay, so 2B, and let's move there. So change directory dot dot means back out a directory, dot dot slash dot dot means back out two directories. And so now I'm in SF code and I want to go to 2B. So I'm going to change what I call it, O2B. Okay, so then I can quickly see my Makefile by saying concatenate the Makefile. So you can see in my Makefile, I have a make all, and I have all of the examples P1, P2, up through P6. Each of them has its own dependency. These are simple, just a single source file. So we're not doing anything too complicated here. And we're compiling, we're ignoring the object code step in this case, because these are simple examples, and simply compiling straight to a binary. Okay, so, and then I have my clean command, which removes all of the binaries. So at this point, if I said make clean, there's probably nothing there. Make, oops. Yeah, so there's an error here because this thing is empty. I don't have anything there. So, all right, so let's look at our first example. So anytime I write source code, I can pretty safely write these two things first. I will want to read and write from the console, and I want to make that convenient without having to write the namespace every time. And then I want a main function, and this should return 0. If you leave that out, it might give you a warning, but it'll still work. Okay. All right, so here now I'm going to just use some operators. So to use operators, let's say I'll declare 3 integer variables, x, y, and z. I'll say x is equal to 4, so that is the assignment operator. I can say y is equal to x. Again, that's an assignment operator. And then I can use a bunch of operators at once and say, let's say y, I'll stick to the example, but y plus 2 times x minus 3. Okay, so here I've used a bunch of operators in a mathematical setting. So you'll notice in C++, we reuse a lot of these operators. So you always have to pay attention to the context, right? Because this is dereferencing a variable as well. And in this case, I'm using it as a multiplication. If I wanted to specify, I have to put in type name. But yeah, we'll get to that later. Okay, we want to print these out. So let's say cout x. We'll send x to the console, a space, and then y. And then we'll end there for now. Just make sure that, okay, so it's clear. We'll run make. Oh, good. So this was the only empty file that I had. I made all of them, but in particular, I made the executable P1. So when I list, I see my P1 there. So to run it, all right, so I assigned a value of 4 to x, and then I assigned the value stored in x to y, and then I printed them both out to the screen with a space in between. All right, let's put in z as well. I run make. It recognizes that I changed p1 ops.cc. So now I have my new, so now I have, oh yeah, I didn't put a space. Okay, so run make again. So 4, 4, and 9. Yeah, this is not as convenient as I thought. Let's see if we can make this so. There we go. Okay, so what happened here? I assigned the value of 4 to y. So this is 4 plus 2 times 4 minus 3. So 4 plus 2 is 6. Times 4 is 24 minus 3 is 21. We got 9 here. The reason for that, as probably most of you are familiar with, is that there's C++ institutes an order of operations to these, right? So this uses bed mass. So brackets, exponents, division, multiplication, addition, subtraction. All right, so it goes through, it does this operation first. That gives me 8 plus 4 is 12 minus 3 is 9. So do be aware of the order of operations. Yeah, if I wanted to enforce an order, I could put brackets around it. And then I get 21. All right, so yeah, nothing too earth-shattering at this point. I can use Boolean expressions. So this will return true or false. And then I could say X and Y are equal. Or else I can output oh my goodness, I did not notice the time. So X and Y are equal. So they're both equal to 4, right, as we have up here. Yeah, we can also do, this is a neat little operator. So I can say, I can combine this if statement into one single statement and say Y equal to Z. So I give it a Boolean, and then I give it the question mark, which is sort of the if. And then if it's true, then I'll output equal. Otherwise, if it's false, not equal. And then, so that is an expression. And then I can put an end line at the end of it. So I've put this in line into my statement here. What happened? Oh, well, see, C++ will let you do anything, even make dumb errors. Okay, so not equal. All right. So we'll end there for today. Next class, we'll go over the basic language constructs, probably stuff that you're familiar with, but we'll look at blocks and, well, we're going to look at some stuff that you don't know. So blocks, expressions, statements, things like that. Standard input output using cin. We're also going to look at parameters for functions, and then passing by reference, passing by value, and references in general. But that's it for today. I can stick around to answer any questions, but otherwise, I guess I will see you guys next week, next Monday. All right.